And you know what else works like addition of real numbers and multiplication by real numbers? Addition of polynomials and multiplication of polynomials by real numbers. Let's do some examples. So let's say we have 1 plus square root of 2x plus pi x squared. We want to add that to 2 minus x plus 3x squared plus x cubed. So we add those together and we get 3 plus square root of 2 minus 1 x plus pi plus 3 x squared plus x cubed. And if we want to multiply a polynomial by a real number, then we have, let's say we want to multiply by -6, and we'll take the first polynomial, 1 plus root 2x plus pi x squared. That is -6 minus 6 root 2 x minus 6 pi x squared. So what we just did is we basically added lists of real numbers together. We added 1 root 2 pi, well, let me say comma 0, so these will have the same size, to 2 -1 3 1 to get 3 square root of 2 minus 1 pi plus 3 1. So it's really the same computation here, except I didn't bother writing the plus signs, the x's, the x squareds, and the x cubeds. And the scalar multiplication I could have also expressed as -6 times 1 comma root 2 comma pi. That gives us -6 minus 6 root 2 minus 6 pi, which are precisely the coefficients we got here. Only difference is, again, I'm not writing the x and not writing the x squared. So that means that if we're just going to add and multiply by scalars, polynomials with real coefficients behave just like lists of real numbers. So if we're just going to add and multiply by real scalars, then polynomials, let's say a0 plus a1x plus a2x squared, etc. Let's say this polynomial has degree n. Polynomials like that behave just like lists a0 through an of real numbers. All we're doing is adding coefficients and keeping the x's as placeholders. And if we multiply by a scalar, we're multiplying that scalar by all the coefficients, and again, the x's are just placeholders. So let me introduce notation for the polynomials. We'll write r bracket x for polynomials in x with real coefficients. And of course, if p of x and q of x are polynomials in x with real coefficients, then so are p of x plus q of x and c times p of x. For any real number c. So you can add two polynomials to get another polynomial, and you can multiply by a scalar to get another polynomial. Now if p of x is a polynomial, then so is negative p of x. So for example, 1 minus 2x plus pi x squared, the opposite of it is negative 1 plus 2x minus pi x squared. And both belong to the set of polynomials in x with real coefficients. We just made the coefficients opposite, and the opposite of a real number is a real number, so it's still a polynomial with real coefficients. Now it's important to remember that expressions like 3 are also polynomials, because 3 you can write as 3 plus 0x plus 0x squared, etc. So it's a constant polynomial. And that means that 0 is a polynomial too. Because 0 is 0 plus 0x plus 0x squared, etc. And of course, the 0 polynomial plus any other polynomial is just that other polynomial, because we're adding 0 to all the coefficients, so nothing changes. And it's probably not a surprise to anyone that the distributive law holds for polynomials. So if we have negative 6 times p of x plus q of x, we could write negative 6p of x minus 6q of x. And similarly, if we have 2 plus 3 times p of x, which is 5p of x, we could also write that as 2p of x plus 3p of x. And the reason this works is that the polynomial is just a list of real numbers. Well, a polynomial in R bracket x is just a list of real numbers, the coefficients. So when we add them, or multiply by a scalar, the usual rules of real numbers apply. The end.